Hello friends, welcome back to our channel Geologica. Today in this video I am going to talk about the Feldspar group of minerals and more specifically about the ionic substitution which is taking place during the growth of these minerals. But before we begin, you can join our Telegram channel Geologica 2020 to get the latest notification or update, and whatever study material I share you can get it from this Telegram channel. You can also contact me through the Instagram ID gupta_99. Now let us see the three important members of feldspar minerals, which are orthoclase, albite and anorthite. So albite and orthoclase makes alkali feldspar series, and albite and anorthite makes the plagioclase feldspar and the solid solution series. Now I am not going to talk about the physical properties or the optical properties, rather I am going to talk about the ionic substitution which leads to the formation of these orthoclase, albite and anorthite minerals. So for this understanding, you know that basic building block of any silicate minerals is SiO4 with a negative charge of -4. So silica has +4 charge, oxygen has -2 charge, so net charge here will be -4. Now minerals like olivine can easily add the 2 Mg atom to neutralize this charge and form the minerals. Now we can also add iron in place of magnesium, that is Fe2. So it also neutralizes the charges and the minerals become the phyllite. Now in the condition which is more complex like sorosilicates, chain silicates, phyllosilicates or the tectosilicates. Now in these type of structures the chemical composition is more complex because the oxygen is now started sharing. So as far as the feldspars are concerned, they are formed as the tectosilicates manner. So what happens in the tectosilicates? The oxygens are shared. So now if the oxygens are shared, what will be the silicon to oxygen ratio? As all of you know, for tectosilicates Si:0 ratio is 1:2. That means now our fundamental the fundamental silicon tetrahedra will be SiO2. Sorry, it will be SiO2. Okay, now this SiO2 will leads to the formation of orthoclase. Now how we are seeing in further slide. So as of now we reached up to the SiO2 as a chemical entity. Now this SiO2 have, if we have the 4 atoms of SiO2, then what it will looks like, either we can write it as 4SiO2 or we can write it as Si4O8. Okay, no problem. Now in the presence of aluminium, what will happen? This one silicon atom is replaced by aluminium atom. Okay, so now the chemical composition will be Al Si3O8, but the charge is now changed. One silicon atom has +4 charge, but one aluminium atom has +3 charge. Means there is an excess of minus charge. So it will be like this. Okay, one negative charge is extra. Now to maintain this one negative charge, there is introduction of potassium, which is, as we all know, potassium has +1 charge. So to neutralize this chemical, the potassium is added and finally our product, which is orthoclase, is formed. Okay, I hope you are getting my point. Now what happened during the formation of this orthoclase? We have substituted silica by aluminium. Now aluminium is less ionic potential than the silicon. That means it is a type of admission. As I have already told in my previous videos, we have the three types of ionic substitution: camouflage, admittance and capture. So this is a admittance type of substitution, but we have an extra charge to maintain this another atom is to be substituted. That's why it is also a coupled substitution. Okay, I hope you are getting the point how from a single SiO4 tetrahedron, how the linkage between the four silicon tetrahedron we comes to the point that is SiO2, and by these four SiO2 atoms here, these five SiO2 atoms, the one silica is substituted with aluminium, which leads to increase one negative charge. To maintain this charge, the potassium is introduced, and finally our orthoclase, that is KAlSi3O8, is formed. Now in the presence of sodium, as sodium having the higher ionic potential, so if there is sodium, then simply what will happen, this potassium is substituted by sodium. So here the formula will be NaAlSi3O8. So this is the transformation of orthoclase into aldehyde is the example of capture type of ionic substitution, because the sodium has more ionic potential. Now we are able to form orthoclase, we are also able to form aldehyde. Now how to form the anorthite? Another or the last question. For the formation of anorthite, let me change to the slide. Okay, so what now at this time we have NaAlSi3O8. Now for the introduction of calcium, the charge is now again changed. We know that sodium has one positive charge, but calcium has two positive charge. Okay, that means if we replace sodium by calcium, then what will happen? It will leads CaAlSi3O8, but with one extra positive charge. Okay, this is 2. So with one extra positive charge. Now to maintain this positive charge, another silicon atom is substituted by aluminium. So now the complete formula will be CaAl2 and Si2. One silica is again replaced by aluminium and oxygen 18. So now the charge is now maintained. I hope you are getting the point how we forms or how the orthoclase, aldehyde and anorthite are formed during the evolution of any rock or the evolution of minerals. So this is the case. Now there is possibility, if there is a availability of calcium and aluminium enough, then definitely anorthite will be formed. Now if there is a availability of sodium, when the calcium and aluminium, when the calcium is now ended up and we have only sodium, then aldehyde will be formed. Now if there is sodium is now exhausted, so we have neither calcium nor sodium, only potassium, then definitely at the last orthoclase will be formed. Okay, so this is all about the plagioclase feldspars and how the ionic substitution leads to the development of different minerals. Now at the last I have told that calcium is substitute the sodium. So this is also a coupled substitution, because to substitute one element we have to substitute other element, maintain its charge. or the maintain its stability. So this is the case. So it's all about for today. Thank you.